Okay, bifurcations. So in this lecture, we're talking a little bit about what a parameter is, how phase lines depend on parameters, which is the bifurcation diagram, harvesting the logistic equation, and maybe a little bit about types of bifurcations. I'm not sure that I actually ended up doing that in this one. So differential equations, they have an independent variable, which is usually t, and we use x later on when we use system of equations, and a dependent variable y, and other numbers and letters. And the goal is to find a solution that gives y as a function of t over some domain. And so exponential growth and decay, dy dt equals ky, logistic equation, dy dt equals ky times y minus 1 minus y over n. K and n are data that comes from the situation you're modeling. So these are called parameters because if you look at different species for the logistic equation, for example, you get different k's and n's. If you're looking at different situations involving exponential growth and decay, you'll see different k's. So if you vary the parameters, what happens to the solutions, right? So what's the phase line for the for this equation? So drawing a phase line, how do you draw a phase line? So there is how you go about finding an equilibrium. And I wrote that out because I want you to write that out because I want you to remember it. How do you draw the phase line? You set dy dt equal to 0, and that'll find you the equilibria. That's where dy dt is equal to 0. And then in between the equilibria, the function is dy dt has a sign. It's always positive or negative, and you want to know the sign of that. So for n equals 1, we have dy dt equals y times 1 minus y. So y equals 0, y equals 1 are equilibria. And so we'll draw the phase line for n equals to 1 out here a little bit. So the phase line is the y-axis. At y equals 0, we have an equilibria. And at y equals 1, we have an equilibria. And what is the sign of this thing? If we look at y's that are bigger than 1, well, if y's are bigger than 1, then this is positive and 1 minus y is negative. So for y is bigger than 1, so this is y prime less than 0. So my arrows go down. For y is less than 0, right, this is negative. 1 minus a negative is a positive, so this part is positive, which means I get a negative times a positive, and a negative times a positive is negative. So also negative. Between 0 and 1, if y is between 0 and 1, then y is positive, and this term is also positive. So y prime is greater than 0 there, and so that's what my phase line looks like. That means y equals 0 is a source, or a stable equilibrium. Y equals 1 is a sink. What about for n equals to 2? Well, I'm going to abbreviate dy dt as y prime, y times 1 minus y over 2. So my equilibrium now y equals 0 and y equals 2. So this is n equals 1. N equals 2. Now we have an equilibrium at 0 and an equilibrium at 2. The same argument that we used shows for the case n equals 1 shows us that this is going to be negative this will be negative, and in between you'll be positive. So y equals 0 is a source in both cases. Y equals 1, y equals 2, those are both sinks. And then for n equals 3, what happens? Well, if we set n equals to 3 in our differential equation, our equilibrium are going to be y equals 0 and y equals 3. By the same reasoning we used here, this will be negative, this will be negative, and this will be positive. So y prime is positive in here, y prime is negative up here, negative up here. Y equals 0 is a sink, as a source all the way through. Y equals 1, y equals 2, y equals 3 is a sink. Okay, so what we can kind of see here is that as we change n, we always have one equilibrium that's at y equals 0 and one equilibrium that's at y equals n. This one is always a sink or stable, and this one is always a source or unstable. And that makes sense, right? If we're thinking about this in terms of a population, n is the limiting population. If we start with any positive amount of animals or whatever, we should end up with n as our final amount. So if we started with 3 as our critical, as our stable population, if we start with too many more, population will decrease to 3. If we start with between 0 and 3, the population will increase to 3. And likewise for 2 and 1. So what's a bifurcation diagram for this? So here's n, here's y. We had n equals 1. We drew that bifurcation diagram, down, up, down. N equals 2, the phase line looked like this, down, up, down. N equals 3, the phase line looked like this, down, up, down. And so we're getting a line of equilibria here. And a line of equilibria here. So if you pick your population size, what's going to happen? Well, you draw the phase line and you get up, down, point of equilibrium here and a point of equilibrium here. So it's a phase diagram. And we're tracking the equilibria, this one and this one, as functions of n, and then filling in the spaces with the directions of y prime. Okay, so here's one that's just sort of a pure math problem. What's the bifurcation diagram for dy dt equals y squared minus k, y squared minus 4? And so here's our parameter k. And so our bifurcation diagram will be k here and y here. And what we want to graph is find the equilibrium as a function of k. So what's the equation for equilibria? Well, equilibria are when y prime equals 0, which in this case is y squared minus k times y squared minus 4 equals 0. And I'm going to draw a little thing here so I don't bleed over too much into my picture. So solving this equation, plus or minus 2, those are always equilibrium. Doesn't matter about what k is because that's just that. And the other term is y squared minus k equals 0. And that gives you y equals plus or minus square root of k. Notice that this is, if k is negative, you don't get any equilibria from this, right? So if k is -1, this equation becomes y squared plus 1. There's no equilibrium. So what are our equilibria? Well, at 2 and at -2, so y equals 2, y equals -2, we have equilibria. So there's an equilibria through here, and there's an equilibria through here. And then y equals plus or minus square root of k, we can graph that. Y equals square root of k, y equals 2. I'll be careful about how I draw these things. Y equals minus square root of k, y equals -2. So these are all my equilibriums. This is my k-axis here. That's not an equilibrium, but these two square root functions and these two lines are. Great. So there's the equilibrium as a function of k. If I pick a particular value of k, then I can figure out what my equilibria are. So suppose we take k equal to -1. What does the phase line look like if k equals -1? So here's my phase line for k equals -1. My differential equation is y squared plus 1 times y minus 2 times y plus 2, right? If you factor the y squared minus 4. So what does this tell me? Well, if y is, this part is always positive. If y is bigger than 2, so that means on this part of the phase line, this will be positive and this will be positive. So it'll be positive times positive times positive. So that goes up. If y is less than -2, so that's down here on the phase line, then this will be negative, and this will also be negative. So we'll get positive times negative times negative. So this will be positive. In between -2 and 2, if y is between -2 and 2, this one will be positive, but that one will be negative. And then this is always positive. So positive times positive means that in between, our phase line looks like that. So we have one equilibrium there, one equilibrium there for k equals -1. And then that means that this one here is a source, and this is a sink. Now the sign can't change, y prime, the sign of y prime can't change unless you cross an equilibrium. So if I go from this side of an equilibrium to this side of the equilibrium, the sign might change. But as long as I stay in this region defined by my equilibrium, the sign will always be negative. So those are all going to be down. This will be down 2, and that will be down 2 because it's all in this region. Likewise, if I just stay above this part, then the sign will always be positive. Same thing down here. As long as I don't cross an equilibrium, right, the sign doesn't change. Because what are the equilibrium after all? The equilibrium are the places where the function is equal to 0. If you're going to change sign, you have to go through a point where the function is equal to 0. So if I move from this region to this region, I'm crossing the equilibrium, and so I might change sign. But if I stay in this region down here, I'm never changing sign. So my phase lines are always like this. And so we know this is a sink all the way up to here, and we know this is a source all the way up to here. In particular, we know this point right here, well, this is down, this is down, this is up, this is up, this is up, this is up. So this is a sink, this is a source, but this point right in there, don't know if I can actually get an arrow into there, but the origin is a node, right? Because we're going down and then going down. So I still have to figure out what the sign is in this region, in this region, and this region. So if k equals, well, we know that this is k equals 4, right? Because when k is equal to 4, then square root of k is 2. So that gives me this intersection and that intersection. So let's take k equals to, what's the number that's got a nice square root? K equal to 9. Right, so 9 is out here somewhere. Y prime is now equal to y squared minus 9 times y squared minus 4. Y prime equals y minus 3 times y plus 3 times y minus 2 times y plus 2. And if you remember how to do sign charts from algebra, right, this is one way to figure out what the signs are. So we know at y equals 9, right, we're going to have a phase line for not y equals 9, for k equals 9. And then if y is bigger than 3, right, because that's the square root of 9, right, that's one equilibrium at y equals 3. If y is bigger than 3, then these are all positive, so we're going up. It should be going up like these. And here we're going up as well. If y is less than minus 3, then these are all negative, but there's 4 of them, and 4 negatives is a positive. But if we go across this equilibrium, right, that means y going from less than minus 3 to just bigger than minus 3, then this one changes sign. So if y is just a little bit bigger than minus 3, this will still be negative, but this will be positive. This will be negative, and that will be negative. So we'll have negative, positive, negative, positive, which means this is down. Then y equals minus 2, right? We're crossing this equilibrium, which is going to change this sign from negative to positive. And then we'll have, oops, that should be a negative. Negative, positive, positive, negative. So that's up in between these. And then when we cross the line y equals 2, this is going to change sign from negative to positive. And then we'll have negative, positive, negative, positive. And so this part will be negative. And then when we cross there, that will change this to positive, and so everything's positive. Great. So now we know that in between the square root and y equals 2, it's down. In between y equals 2 and y equals minus 2, it's up, down here, up there. Fill in this last one, down, up, down, up, 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 down, up, up, down, up. So what does that make this this equilibrium here, right? Everything's fleeing away from it, so that's a source. This equilibrium here, everything's flowing into it, so this is a sink. Everything is flowing away from this one, so that makes this a source, and everything is flowing into this one. That makes that a sink. So what about these 2 points right here and here? So when k equals 4, we know this is up. We know this is up because we know that these are all up in between y equals 2 minus 2, and these are up. So these two things are nodes. And then finally we have in here, up, down, up, down, up. So kind of a messy diagram, but we can simplify that a little bit. So we have y equals 2, y equals minus 2, and then we have y equals square root of k, and y equals minus square root of k. There's our equilibria. We know that this is a source out here. That means things are going away from it. This is a sink here. That means things are going into it. This one's a node. Stuff is going down and down, and still up and away. So that's a node at 0, 0. This is continuing as a source. This is continuing as a sink. What about these things? Well, in between here, right, we're actually going, everything is going up in here. So we're going up to this one and up away from that one. We know that outside of everything, we're going up, and outside down here at the bottom, we're still going up. So what about this equilibrium here? Well, we're going down towards it, and this is going up. This is going up. This is going up. This is going down. This is going up. So this stays as a sink all the way to here. This stays as a source, y equals 2, all the way to here. This starts out as a sink, right? Because everything's going into it. This starts out as a source. These two are nodes because we're going up here, up there, and up there. So that's a node and that's a node. And then out here, we're going down and down, down, down. That makes this one now the source, and this is a sink. So what happened is, we'll label this one, this is also a source. This is a sink. As k changes, right, as k increases, we go from left to right. We start out with a source and a sink, and they just live happily, blah, 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 until k equals 0. And then this is born, a node is born there. And as k goes past 0, we now have our source and a sink. But we also have this new sink that came out of the node and this new source. This sink and this source collide right there. This one becomes the source, and this one becomes the sink. This source and this sink collide right there, and they transfer properties. This becomes the sink, and that becomes the source. So there's a bifurcation diagram, a little bit complicated, but really you just graph the equilibrium as a function of k, right, which is just setting the derivative equal to 0 and see what your curves are, and then figure out what the sign is of y prime in between the curves. So here's a graph of a function, f of y, which is the right side of a differential equation, dy dt equals f of I. What's the bifurcation for this? Well, we know that c is a parameter. And what it does is f of y plus c moves graph up and down. Okay, so when we're looking at this graph, this is y on the horizontal axis. This is y prime, right, my dy dt, and this is my function y prime equals f of y. So if I tell you what y is, if y is 2, then that tells you y prime is 0. If y is 1, then y prime is 0. If y is minus 1, then y prime is 0. So for c equal to 0, what do we know? So here's my parameter c. Here's y. C equals 0 is the y-axis. We want to know what is the phase line along the y-axis. Well, minus 1 is a root, and so that's where y prime is equal to 0. So is 1, so is 2. So these are all equilibria. So minus 1 is an equilibria, 1 is an equilibria, and 2 is an equilibria. What we see between minus 1 and 1 is that y prime is always negative, right? So this is the graph of y prime. It's less than 0, right, below the y-axis, if we're between plus 1 and minus 1. So negative there. If we're between 1 and 2, we're still negative, so negative there. If y is bigger than 2, we have a positive y prime. And if y is less than minus 1, right, so my y's are here, we still have a positive. So there's y. There's the phase line for y equals 0. That's this graph. If I make c positive, what does that do to this graph? It's going to bring it up. So if I raise it a little bit, I get something like that. What does that mean? Well, my equilibrium moved from minus 1 up a little bit, from 0 up a little bit. And this equilibrium actually split into 2, right? It gave birth to one over here. Oops, sorry about that, that's not there. This one split into 2. It gave birth to one over there, and it gave birth to one over there. And then this one moved in a little bit. So if this is my new C, a little bit positive, I'm going to have an equilibrium that's a little bit higher than minus 1. So this equilibrium is this one here. I'll have one less than 1 and one bigger than 1. So here's 1. So I'll have an equilibrium here and an equilibrium here. That's this one and that one. And then I'll have an equilibrium a little bit less than 2. That was this equilibrium. So I'll have an equilibrium like that. So 1, 2, 3, 4 equilibriums. There's my phase line up there, negative between those two, positive in here, negative down here, and then positive down here. Now, if I raise it a little bit more, what happens? Well, this comes down, and this will intersect in there somewhere, and then this will just touch the y-axis, but not go through it, and then go up. So if we increase C a little bit more, what do we end up with? We still have an equilibrium out here, but then these two have actually run into each other, right? That's at that point. So those have run into each other, and then we go up. So we actually have an equilibrium here that's just one there, and then one there. And we know that for our phase line, this is still going to be positive. Well, did I lose track of one? 1, 2. There's a third one in here. That's this one. So positive, negative, positive, positive. Great. And if we keep raising C, eventually we'll touch there. And then this one won't actually come down to the y-axis at all. It'll just keep going up. So we'll just have the one equilibrium there, and the whole thing will be positive everywhere. And if we keep raising it, then the graph eventually just doesn't hit the y-axis at all, and it's just always positive. So what does that mean? Well, if we think about this root and this root, as we raise this minimum, these two roots come together and then they bonk into each other and then it vanishes. So that's this root and this root. So they should actually bonk into each other down here. So these x-intercepts, this one, this one breaks into two and we go out this way, and then they meet and they break up. What about from here and here, right? We have these two. And as we increase C, these two run into each other. And then when this minimum goes through the y-axis, they disappear. Not quite sure where I drew that in, but something like that. And that's where we ended up with these nodes, right? When we're actually just sitting on the y-axis there. And if we raise the graph far enough, right, it doesn't intersect at all. What happens if we push it down, if we have a negative C? Well, if we have a negative C, this graph, this equilibria goes to the left. When this maximum pushes down away from the y-axis, that just goes away. And then we have this one moves out to the right. So we end up with just one out here and one out here. And so our bifurcation curve will end up looking like that. Right? So as we move this graph up and down, right, the equilibria are the x-intercepts, right? As you move it down, you lose this one. As you move it up, this will split into two, and then we'll get a node when this hits the y-axis, and then we'll get another node when that one hits the y-axis. Okay. So bifurcation diagrams track equilibria as a function of the parameter. Sketch the bifurcation diagram for dy dt equals this. And so this is sort of directions about how to sketch a bifurcation diagram when you get a problem in the homework. So harvesting and the logistic equation. So here's an example. Fish population length has a growth constant k equals 3, carrying capacity 60,000. The DNR wants to set a harvesting rate h fish per year that doesn't overfish the lake. So what's the model for the fish population in the lake? So a logistic curve tells you, and this is a simple model, but it, oops, don't know what's going on there. dy dt equals 3, because that's my growth constant, y times 1 minus y over 60,000. That's the basic model for a fish population, right? With harvesting, though, we want to be able to take out h fish per year. So dy dt, the effect of harvesting should be negative on dy dt by however many fish we're taking out. So there's the rate of change of the population of fish. This term is because the fish breed and grow more fish. This term is saying that whatever lake they're in has a capacity of about 60,000 fish. If there's more than that, the fish will die off to get back down to 60,000. If there's less than that, the fish will rise in population to get to 60,000. And then this is how much we take out of the lake by fishing. So what is the model for the fish population in the lake? So what's the bifurcation diagram? So what we want to do is solve this equation, to get the equilibria, right? We set that equal to 0, and we try to solve for y as a function. And I put a question mark after function because it might not actually be a function. There might be multiple equilibria depending on which h we're looking at. But we want a graph with h as a horizontal axis and y as the vertical axis. So you can do that by hand, but the easiest thing to do is to go to GeoGebra and make GeoGebra do it. So I'm going to use x for h, right? Because GeoGebra likes everything as x's and y's. I want h to be my horizontal axis. So what I want to graph is 3y times y minus 1 minus y divided by 60,000. 1, 2, 3 minus x. Nope, not inside the parentheses. Minus x. Remember, x is my harvesting thing, equal to 0. And I get that, and that's not very useful. And that's not very useful because 60,000 is a huge number. So I need to adjust my axes. So let's put the y maximum to be, I don't know, 70,000. There we go. And let's make the x maximum to be, say, 35,000. Great, is that good? Make this minus 1,000 so we can see what's going on. And we'll make x max actually up to, say, 50,000. There, so there's our graph. This is our bifurcation diagram, right? These are the equilibria. The green line are equilibria. The x numbers are fishing quotas, right? So if x is 30,000, that means we're taking 30,000 fish out of this lake. And so this blue line here, that's going to be our phase line for a harvesting rate of 30,000. So if we look at this curve, if y is really, really big, right, and x is just 30,000, and we look at the green equation, that means we'll have a negative value, right? Because if y is bigger than 6, if y is a large number, right, 1 minus this will be negative, that would be positive, this is negative, so negative minus something, that'll be negative. So if we're thinking about drawing a phase line, the arrows here on equation on the blue line will be down, and then in between would be up, and below would be down. So this point is a danger point for the DNR, right? If the fish population gets down to 12,680 roughly, or if it drops below this, well, 12,679, then you're over harvesting. Your fish population will drop down to 0. Okay. As long as your fish population is bigger than that, it'll settle back to whatever this point is, 47,320 fish, more or less, as a stable population. But you have a problem here, right? Because if the population should crash for some reason and you go past this, then you have to throttle back on the harvesting because you might run out of fish. If you make the harvesting rate too big, say 45,000, then you're at your node, right? If your harvesting rate is 45,000, you have a stable population of 30,000, right? But all the arrows on our bifurcation diagram will be pointing down. And so if you overharvest a little bit, your population crashes. So let's go back to our lecture notes and sketch that. So what we got from GeoGebra was that if H is our harvesting rate, we got a curve that looks like that. This point was at a harvesting rate of 45,000. And this was down, and this was down. And if you harvest too much more than that, right? If you harvest more than 45,000, you're just overfishing the lake. If you had a harvesting rate of 30,000 though, right? That would go down, this would go up, this would go down. This is a stable population as long as you keep your fish above this level, right? If the population goes down by that level, you have to decrease the harvesting rate so the fish population can build back up. But this is where you want to be able to keep it. The DNR, of course, has much more complicated models for fishing, right? But this is one of the ways they sort of go about figuring out what the limits on various lakes could be, right? Is you look for, as we change the harvesting rate, what happens to the fish population. So this is just saying a constant amount of fish. We take out 30,000 out of this particular lake, whatever this lake is, of this particular fish. And you know, you're okay as long as it doesn't go below, I think that's something like 12,000. A different model would be to say H times Y fish per year that doesn't overfish. So what does that look like? And I actually want this also to be 60,000. So we'll go back to GeoGebra. It's my GeoGebra, there we go. We'll get rid of this and we'll just say, okay, our equilibrium now, 3y times y minus y was 60,000. X is still our harvesting rate, but we want to change the model so it's x times y. And we'll see what that gives us. And that gives us something that's hard to see because you can see there's some green lines there, but our scale is kind of screwed up. So let me change the scale a little bit and we will see what we get. Okay, so there I've tweaked with the numbers a little bit so we get a decent picture here. Note that the x coordinate is now at 3, we get this intersection, and then so 9.5 out to the right. The y coordinate still goes up to 60,000. So again, if x is equal to 0, we still have 0, and 0 and 60,000 is equilibria. 0 is always going to remain as an equilibrium because if we set y equal to 0 throughout, we get an equilibrium. And then we also have this line, which is the other equilibrium. And so if we set x equals to 2, for example, right? What does that tell us? Well, if y is still really big, right? This will be negative. So along this phase line, we would have a negative slope up here. In between the two equilibria, we would have a positive slope, and down here we'd have a negative slope. So at this point, you'd have a nice stable population of about 20,000, and you'd have a little bit of space below. If the population goes down to 10,000 or even 5,000, it should build back up. So what we don't have here is that equilibrium that we had underpinning our harvesting rate. When we get to y equals 3, however, I mean x equals 3, a harvesting rate of 3. Oh, sorry, we wanted 3 there. Harvesting rate of 3, right? We actually get our node because this is going down and that's going down. So what is this numbers on the x-axis, our harvesting rate here? Harvesting rate actually is being compared to the rate of reproduction of the fish. If we're taking out fish at a rate of 3, x equals 3, that means we're taking out fish at the same rate they're being reproduced. And so the stable population will be actually equal to 0. If it's 2 or 1, then they're reproducing fish a little bit faster than you're taking them out, and so you grow up to a stable amount. So a different model that one can do for using fish, but again, if we think of x as our parameter that we're setting, Right, we can change X as the harvesting parameter and get different stable populations for our fish. So let's go back to that diagram. So what does this diagram look like? No, there it is. So this is one equilibrium, and this line is the other equilibrium. We know when H equals 0, we have that. And so this is our bifurcation diagram. I got all the arrows backwards. Down, up, down. This should be up. That should be down. That should be down. And then at 3, right, that's a node. So this is a source. This is a sink, right? Populations tend to go to sinks. When we get to the node, though, this is down, this is down, but this will be up. This will become the sink. This is a source, but once we're down here, this is a negative equilibrium and you can't have negative fish. So y equals our harvesting rate of 3 is the danger point for this particular model. That's why. Okay, so bifurcation diagrams help us sort of model how you should actually figure out how many fish people should be allowed to catch in their lakes.